we're going to study potential energy of springs, okay? Or I don't know of another word of spring. Elastic, they call them, like a rubber band or things like that. Elastic potential energy or spring potential energy. Those two things mean the same, okay? So elastic and spring mean the same. And in order for us to really get into this first, I want to make sure we're comfortable with a couple of vocabulary terms. If a spring is static, does that mean it has any sort of stretch or compression to it? It does not, right? It's at rest. We also call this equilibrium. Equilibrium, okay? We also call that equilibrium. So when a spring is just at rest, not stretched and not compressed, we consider it to be an equilibrium. And then we know that when we're compressing a spring, we're pressing it together, and when we stretch it, we pull it apart. What does a spring want to do? It wants to be static. It wants to be back to its equilibrium point. So when we stretch a spring and we let it go, what will it do? It will shrink back down, right? It will go back to its point. When it is being stretched or compressed, what type of energy does it contain? Kinetic or potential? Do you think is it moving, or does it have stored energy at that point? It has stored. So it has potential energy. Anytime it's at a place of stretching or compression, it has spring potential energy or elastic potential energy. Okay? It could be in motion on its way from stretch to equilibrium, and they would have both, right? It would still have some stored energy and it's in motion, so it might have both. But we see that elastic spring potential energy get transferred into other things. Like think about the spring of a pen, right? We transfer the energy into the tip of the pen and it moves, right? Or on a trampoline, you jump and that energy transfers to you and you go higher, right? Those are things that energy is transferred. So we take that stored energy and we're usually moving it on to something else, okay? So here's our equation for potential energy of a spring. Potential energy is equal to 1/2 kx squared. It looks very similar to what equation? Looks very similar to our kinetic energy equation, doesn't it? Ke is 1/2 mv squared. This is 1/2 kx squared. Okay. This is an equation sheet thing. I would agree. This is a big one. Okay. Potential energy of a spring. So I might even write it like this. Pe of a spring is 1/2 kx squared. Now, maybe you're asking yourself, what's K? That's a new one, right? It does not represent kinetic energy. Kinetic energy is a capital K, and this is a lowercase k. And what it represents is what we call the spring constant. All right, K is equal to the spring constant. I wish, for our sake, it actually meant it's constant, but it's not. Every spring has its own spring constant. So it's not really a constant at all, okay? So it's a little misleading, but it's a value that's assigned to every spring. So slinky springs, very, very low K value, right? It doesn't take a lot of force to make them move. But like car suspension springs, car shocks, very high K value, right? It takes a lot of force for them to stretch or compress. So the way that the K value is calculated is with this equation. Oops. And you don't have to write this down yet. We might get to this later. Maybe soon. I don't remember. F equals Kx. And what this says is the force that it takes to compress the spring this distance is going to be equal to the K value of that spring. That's really how that value is calculated. So like I said, the tougher the spring, the higher the K value. Okay, the flimsier the spring, the lower the K value. Okay, so K is spring constant, but X is the distance the spring has been stretched or compressed from its starting point. Now, a lot of times we will get this value in centimeters, but it needs to be in meters. So we want meters here. We want meters. It's rare that we're going to compress a spring a certain number of meters, right? But we need to convert that. And what do you think we might forget while we're doing our problem? The square. We might forget. You guys won't. You'll never. But I might forget it, okay? So you got to make sure that we see that square in there and we don't forget, okay? So now that we've kind of introduced that, we're not going to run any problems just with springs because this is just like plug it in and get it out, right? But we're going to move into our transition into talking about conservation of energy. All right. And to get there, we're going to learn about something called the total mechanical energy of the system. Total mechanical energy is essentially just the sum of all the potential energy and all the kinetic energy at one point. So if an object is moving and it's high off the ground, like let's say something's in free fall, like right here, right? It's moving downward. It would still have potential energy because it's off the ground, and it would still have kinetic energy because it's in motion. So the total mechanical energy is the sum of potential and kinetic at that point. This is not an equation I think you need to put on your equation sheet yet. I'll let you know when we get there, okay? This is the energy at one point. But if we're looking at the conservation of energy, we want to see how does the energy at one point, is it equal to the energy at the second point? That would prove conservation for us, right? If the amount of energy at the beginning of the roller coaster is equal to the amount of energy at the end of the roller coaster, that would prove to us that energy is conserved, right? It wasn't lost somewhere along the way. Now, remember, we get to live in perfect physics world. So we get to ignore friction and other things that could dissipate energy through a real roller coaster ride. Are we on the same page there? Right? We're living in perfect physics world. So what we're trying to examine is energy at the beginning and at the end the same? So the way that we do that, put energy at the beginning equal to energy at the end. Okay? And I'm going to talk here for just a second. You don't have to write just yet. Give me a second. We're going to go from energy at the beginning to energy at the end. All I did here was sub. If mechanical energy is kinetic plus potential, then energy at the end is kinetic plus potential. And then all I did from here was sub in their full equations, right? This is still kinetic plus potential equals kinetic plus potential. What do you think the ones and the twos mean down here? Yeah, it's like initial and final. Okay, you could write an I and an F if you wanted to. But I don't know, for some reason this one just uses first and second, right? But we're looking at all of the energy before and all of the energy after. So this big guy, he needs to go on your equation sheet, okay? This one needs to go on your equation sheet. This equation is assuming that we are having potential energy due to gravity, not potential energy of a spring. If we were dealing with springs, we would just sub in 1/2 kx squared right here instead of mgh, right? If we were using springs, but if we're not, then we're just going to keep it with gravitational potential. Okay, so this one needs to go on your equation sheet. The good news is that there's not every scenario do we have to use all four of those terms. If we start out with a situation that's only potential energy, then this would become a zero and we'd get rid of it, right? So it just kind of depends. We won't always use all terms of our equation. It's situational, right? I like to write them all out so I know I thought about them, but we won't necessarily have to use all four parts of it every single time, okay? And remember we talked about earlier, we get to kind of shift our frame of reference. So that might help us be able to mitigate some of this messiness as well. Okay, so are we ready to try one? Okay, this is just a reminder here. As we're looking at objects that are falling, at objects, remember I said this chapter loves to use a roller coaster. Okay, we love it. So as we're looking at our path of our roller coaster or our path of something falling through the air or whatever it is, when we reach this low point right here, right, we essentially get to call this the ground level. And so let's kind of walk through our types of energy here, okay? Let me back my roller coaster cart up just a little bit. Let's say that I'm here. I've done the tick, tick, tick of death, you know, da, 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 da. I'm at the top now. I'm waiting. I'm paused, not moving. So at this point, I would have all potential energy. As we plummet, what type of energy do we have? If I'm looking at it here, what type of energy do I have? Kinetic potential or both? Both. I have both. Because at this point, I'm in motion, which means I've got kinetic energy, and I'm still not to my low point yet. So I would still have gravitational potential energy. So I still have both at this point. But what about when I get to the low point right here? Oh, I'm off the tracks. That's what I'm afraid of, people, you know? Okay, what kind of energy would I have here? All kinetic. Okay, so that's what this point is telling us here, is that just before the object hits the ground, all of the potential energy will be transformed into kinetic energy. So it's a transformation that happens. I want you to think of it, remember, as like a pie chart of energy, right? If it's all potential, that means it's non-kinetic. And if it's part-way kinetic, then that means the rest of it is potential, and so on. Okay? All right, let's try one here. This says, if a stone being held at a height of 3 meters, calculate the stone's speed when it has fallen to 1 meter above the ground. So let's draw out a little image of what we're talking about here. Here's our object. It's going to fall to be here. Here's the ground. This starts out at 3 meters, and this is 1 meter above the ground. Agreed? Now, could we use kinematics to solve? Yeah, but we're not going to. Okay, we're going to use this one for right now. But in, later circumstances, you can choose whatever you want. So we need to start thinking about what types of energy does it have in these situations. If it's being held at 3 meters, what type of energy do we have here? Kinetic, potential, or both? All potential. So we've got all potential energy here. What about at this height? It's a meter off the ground, but it's still falling. It has both. Okay, so it has kinetic and potential. Okay, and it doesn't even ask me about getting all the way to the ground. So I'm just stopping there. Those are my before and my after. Are we good with that? Okay, so if I start thinking about conservation of energy, I've got an equation that says kinetic plus potential equals kinetic plus potential, right? This is before and this is after. Yes? Okay. And I already said that at the beginning of my motion, I have all potential, which means this kinetic energy is 0. So I don't even need to bother putting that into the equation. Okay, the next thing that we're going to do is we're going to plug in the potential energy. Now, do we have potential energy due to gravity or potential energy due to a spring? Gravity. So we're going to plug in M times G times H. Are you seeing red flags here? Are we seeing red flags? We're trying to calculate the speed, but what else are we missing? We're missing mass. So just hang on for a second. Okay, we're just going to hang on. We're going to keep it plugged in as M. So final, we said it has kinetic energy, so that's going to be 1/2 mv squared plus M times G times the height, which is 1 meter. Okay, so we've got 2 variables here. But let's see how it goes. Let's just keep working our math out, okay? So let's start simplifying some things here with our math. 9.8 times 3 is 29.4 m equals 1/2 mv squared plus 9.8 m. Am I able to combine my like terms here? Yes? Can't I subtract this to the other side? 9.8 m, 9.8 m. Happening. We're going to subtract that to the other side. Okay. 19.6. 19.6 m equals 1/2 mv squared. So what can I do with my m? If I have an m on both sides of my equation, what can I do with it? Yeah, I just divide by m, which essentially cancels it, doesn't it? Right? It's like having an x on both sides, right? I can get rid of it. I can cancel it. So that's what I do. And so what I'm telling you here is that mass doesn't end up being a factor, right, for problems like this. So I'm going to say 19.6 is equal to 1/2 v squared. So I'm going to take 19.6 divided by 1/2 and square root, and I get a value of 6.26 meters per second. Now, what's true about my object here? Is it going up or is it going down? Down, so I have to add the negative there. I only have to do, I'm only asking you to add the negative in situations where it's in free fall. Okay, in situations where it's in free fall, I want you to add the negative. If it's on the roller coaster and is moving forward, we're just going to call that positive. But objects in free fall, I want to add the negative there. All right, assuming the height of the top of the roller coaster is 40 meters and the car starts from rest at the top, calculate the speed of the car at the bottom of the hill. And then at what height will the car have half of this speed? Okay, so let's kind of draw out what's happening here. Here's our roller coaster. This has a height of 40 meters. We want to know the speed of our car at the bottom of the hill. So again, we're going to kind of track here. What type of energy do we have in each scenario? At the top, we have what? All potential. And at the bottom, we have all kinetic, right? We're under the assumption that it cannot fall any farther, right? We're assuming it's staying on the track, okay? Can't fall any farther. So that's been all transformed into kinetic energy. So if we go look at our conservation of energy equation, I'm going to bring it down here at the bottom. I'm going to come in here. If we look at our conservation of energy equation, it's kinetic plus potential equals kinetic plus potential. But what did we say at the beginning? We have no kinetic. We have potential of mg. What's our initial height here? 40. And at the end, we said we have all kinetic, 1/2 mv squared, because I'm solving for v, and we have no potential, so plus 0. The reason I like to plug in those zeros is so that I know I thought about all 4 terms, right? I'm like checking myself to make sure I know there's no kinetic at the beginning, and I know there's no potential at the end, so I plugged in a 0. Okay, so now we're just looking at the math. 9.8 times 40, ooh, bless you. 392 m equals 1/2 mv squared. What happens to my m's here? They go away. So 392 divided by 1/2 and square root gives me a velocity of 28 meters per second. And because this object is not in free fall, I'm not going to put the negative on there. I'm just going to keep it positive because it's moving forward, right? It's moving forward on a track. How about the math here? Did we get it to come out?
I got 14.
You got 14.
It's 392 divided by 2.
No, not divided by 2. It's divided by 1/2. Okay, that's okay. Okay, any questions with how we came out with this one?
After there was 28.
Okay. So the next part of the question says, at what height will the car have half of this speed? So what's our prediction? Is it halfway down the hill? Yeah, halfway down the hill would be a fair prediction. So let's see if that comes out, okay? So if now we're looking at kind of establishing our roller coaster, not at the bottom of the hill, but at some point in here. Right? We know it's going to be somewhere in the middle. We're not really sure where. We're looking at it at some point. But we know that at some point in the middle, what type of energy is it going to have? It's going to have both. Okay, so now let's come look at our equation again and say we have kinetic plus potential equals kinetic plus potential. In all reality, if I wanted to, I could examine the end to the both if I wanted to. You could pick any 2 points during your path. It's just easier for me to go back and use the beginning one, right? So I'm going to go from the start point to the middle point and find out, what am I really solving for here? I'm solving for height, okay? So we said at the beginning we have no potential. We have no kinetic. We have m times g times h. And then at the end, we said we do have both. We have kinetic plus potential. Do I know my velocity at my halfway point? half of this speed, right? I solved for my speed at the bottom, but it's saying at what point will I have half of my speed? So what is my velocity here? 14 squared. Good. Plus mgh. And I'm solving for height. Now, what do I know about my masses? What do I know about the mass? It will eventually go away. So if you don't want to write it in there, then don't. If you're given a mass, I would include it, but it really is not going to make a difference. Okay, go ahead, Maddie.
Why did you add them together instead of
Oh, that's a total mistake. Thank you for pointing that out. This should be an equal sign right here in the middle. Thank you. All right. So this side is still going to be 392 m equals 98 m plus 9.8 mh. Then I'm going to combine my like terms. 294 m equals 9.8 mh. So now I'm to an algebraic point right here where my m's do go away. Okay, so I'll take that divided by 99.8 and I get a height equal to 30 meters. Let's make sure mathematically everybody can get that to come out. That the cart has traveled 30 meters downward, or that it's traveled 10 meters downward? What's that tell us?
10 meters downward.
Only 10 meters downward. It's at a height of 30 meters off the ground. That's what that's telling us. So that means that proves what you experience when you go on a roller coaster. In the first fourth of your drop, you've picked up half of your speed already, right? That's why you feel this rush, right? The physics tells you that you've already gained half the speed you're going to gain in that first quarter of your drop. And it has to do with this square right here, right? Mathematically, it has to do with that square. But I think that it proves the experience, right? It mathematically shows you that experience you feel is true. So that's kind of cool. Not that I experienced, but you all, okay? Tell me what questions we have here. 1/2 kx squared. And then here we're looking at the kinetic energy that the dart houses, right? And no potential energy left over. So again, we could just take these terms completely out because we have no kinetic and no potential energy at the end. That's really up to you how you want to annotate that. But essentially what we're looking at is pure potential energy being transformed into pure kinetic energy. So let's go ahead and put our numbers in, okay? 1/2 times k, it gave us our k value right there, 250, times x squared. So am I going to use 6 here? It's in centimeters, so I need it to be in meters. Okay, so 6 centimeters is equal to 0.06 meters, right? We divide by 100 there. 0.06, and we want to square that. Equals 1/2 times the mass of the dart, 0.1 times v squared. Any questions with where our numbers came from there? All right, we looked at our dart and our spring situation, and we knew that it was going to be a transformation of pure potential energy to pure kinetic energy. And so we were able to put that into our conservation of energy equation for that scenario. Now we'll plug it in and see what we get. I got like a nice, pretty whole velocity. Tell me what you got. I got a velocity equal to 3
There we go.
meters per second. All right, try this one on your own. So it's still giving it as the height. So it's 6 meters off the ground. So in this first scenario, that's the way I did it right here. And it's saying, here's the tree, here's the roof of the house, right? And here is the ground. Okay, so this is saying this height of the roof is still 6 meters off the ground. This height of the tree is 13.3 meters off the ground. So you're still going to keep them both as positive. What I did for the second scenario was I just reset this to be my ground level, the roof height to be my ground level. And I said the difference in these is 7.3 meters. And so that's what I put in for my height. And then I didn't have to have any potential energy at the end because essentially it was on the ground, which was the roof. You can do it either way. Okay, do you want me to say that again? Okay, here's what I'm going to explain for this. There's two scenarios here. I ran them both, and you can see I get the same answer for both. Okay, in the first scenario, I treated the ground as ground level, meaning the tree was 13 meters off the ground, the roof was 6 meters off the ground. So that's what I plugged in for their respective heights. Okay, but in the second scenario, I've shifted ground level to be at the height of the roof. And now instead of the tree being 13 meters above that, it's only 7.3 meters above that, right? I just subtracted the height, which is what you did when you subtracted it over here anyway, right? Mathematically, it's the same, but I had to maybe do a little bit less work because then I'm saying, no, I don't have the potential to fall any farther because that's my ground level. Okay, so we kept the ratio intact, but we were able to shift, right? We're able to have a little flexibility about where our frame of reference is. So I moved my reference to be the roof height, and so then I really didn't need the 6 meters except to know that that was the difference in my height value. So there I put it, my original height is this, and then final, I didn't have any potential energy because I'm on the ground at that point. So you can do it either way. Questions with that? Yeah, go ahead, Mary.
Why did you put potential